Bismillahirrahmanirrahim. Assalamu alaikum. It's our 25th lecture on advanced electromagnetic field and waves, and in this lecture we are going to solve next section of chapter number 10, which is scattering from perfectly conducting surface. We already did scattering from dielectric sphere in our previous video. If you forgot to watch, you can watch that video first, then move on towards this video. In this, we have to solve scattering from perfectly conducting spheres. Okay? Perfectly conducting. What does that mean? If your cylinder is perfectly conducting, it means your field inside is zero. Okay, so you can easily apply the boundary conditions, tangential boundary conditions of electric field, because field inside is zero. So let's suppose this is your conductor. Basically, you can see this is your conductor having, this is x direction, this is y direction, and inside is the z minus z direction, and this is the positive z direction. What is basically your incoming wave electric field is propagating in the direction of y. Okay, your electric field is propagating in the direction of y, because this is your cylindrical coordinate system, and we know that in cylindrical coordinate system your x equals to rho cos of phi. uh, the minus z direction and the x direction makes an angle 90 degree. Okay, and there is a radius from the center to the sphere. There is a radius, let's suppose this is a is the radius of the cylinder, and the distance from x to that radius angle is making phi, rho. Okay, phi is this, rho is this. So the x component becomes x equals to rho cos of phi. And in general, we know that for plane wave, the electric field can be written as, because electric field is going propagating in the z direction. Okay, so here you can see z direction. Okay, and E naught I, and your the propagation of wave is in the x direction, as I mentioned you here. The propagation of wave is in the x direction, electric field in the z direction, and propagation of wave in the x direction. So that's why your plane wave equation now becomes E of I equals to z cap, E naught I, which is the amplitude, and e power iota kx. As I mentioned you before, x must be equals to rho cos of phi. So you have to put the value of x rho cos of phi. So it becomes this z cap E naught I e power iota rho cos of phi. This is the electric field equation for plane wave, but we are solving cylindrical coordinate system, and the use of plane wave is unnecessary. So you must have cylindrical waves. So you must have to convert your plane wave into cylindrical wave to solve this problem, because your body is cylindrical and wave is plane. So this is not the case. You must have to convert your incoming wave in the cylindrical coordinate, in the cylindrical wave. And you know that how you can convert, by using Bessel's functions. Bessel functions are basically the cylindrical wave functions. So you have to write your electric field equation in terms of Bessel functions, because Bessel functions are the cylindrical wave functions. So it can be written as this, like this. Okay, incident wave is plane wave and body is cylindrical. Thus we have to convert plane wave into cylindrical wave by using the Bessel functions. So this is the equation EI equals to Z cap E naught I, which is same, direction is same. Now the only thing is summation from minus infinity to infinity I power minus n j of n k rho, where j of n is Bessel function of first kind, and there is also Bessel function of second kind, which is denoted by yn or nn. Okay, so jn k rho e power n phi. So now you're successfully electric field in the cylindrical wave. Okay, now this is the equation of electric field, and you don't need any aspects inside, like E naught I. You have to need equation in term of E naught I. So that's correct. The only thing is now you have to find the H of I, means incident uh, magnetic field. How you can find? By using the Maxwell's equations. You know that Del cross E basically equals to minus partial B by partial T, and partial by partial T when it converts into minus iota omega, and outside a minus, so minus minus plus, so it becomes iota omega, and B opens with mu naught H. So del cross E basically equals to iota omega mu H. Understood? Now you can see, if you want to find H, you have to move this to the other side. Del cross E. Okay. So how you can find del cross E? In You can say that in Cartesian coordinate you can find easily, like x, y, z, and other aspects you can easily write. But this is our cylindrical coordinate system. The formula is different. Let me show you a general formula for this. You can see this is basically the general formula. This is the coordinates. In Cartesian coordinate system, your small length element can be written as this: x dx, y dy, z dy. But in Cartesian coordinate system, your small and length element can be written as rho d rho, phi d phi. But inside is a phi, is a rho, and z dz. And in spherical coordinate system, you can write your small nth element as r, because the elements are r theta phi. Okay, r dr. Okay, similarly here you can see for phi, r cos of theta sine of phi d phi, and for theta is basically r square sine theta d theta. So these are the length elements. A general formula to take cross product with del is this: here is 1 by h1 h2 h3, whereas in general this formula you can see dl must be equals to u1 h1 d du1 u2 h2 du2 u3 h3 du3, whereas h1 h2 h3 are the components with this unit vector. Okay, here is 1, here is 1, here is 1. So that's why in Cartesian coordinate system you take as x y z, and here there is nothing because 1 by 1 is 1. But in cylindrical coordinate system, here is 1, but in unit vector there is 1, but here unit vector has a row. So here you have to take only row. Here you have to take phi cap, but with phi cap there is h2 which is row, so h2 you can see here, and there is h3 is basically 1 here, so that's why only z. So that's why I'm telling you, you can write it as like this. Why 1 by row? Because h1 is 1, h2 is row, h2 is there is a row, and so that's why h1 1, h2 row, h3 1, so all multiply it becomes 1 by row. Okay, and here as I mentioned row phi z, but here is a row factor, that's why. And below is basically just derivative of that unit vectors. So here is unit vector row, so partial by partial row, here phi partial by partial phi, here z partial by partial z. Okay, and you can see that there is no x or y component in the formula, only z components. So x component is 0, y component is 0, and your electric field is in the z direction, so that's why E of z. Now you just have to take the cross products, have to solve this by using determinant method. Okay, so 1 by row as it is, row take common, and you have to multiply this by this and minus this by this becomes 0, so only this by this. So here partial Ez by partial phi. Okay, minus rho phi, this by this, so partial Ez by partial rho, and this by this, here 0, so it's 0, minus z, sorry, plus z, this 0 0, so there is no z component. So this is final determinant. What there is, the terms you have to find is this: partial Ez by partial phi and partial Ez by partial rho. So here how you can find. Okay, so you have to take the derivative of E of z with respect to phi. This is your E of z. You have to take derivative with respect to phi, and then you have to take same equation derivative with respect to rho. So let's take derivative. So E naught is constant, this constant, and E iota power minus 1 as it is. But here we have to take derivative with respect to phi. But when we take the derivative, we only take the derivative of this term, because only here is phi. All other terms are constant, they come outside. And when we take derivative of this, it's become e power iota n phi, and derivative of the power which remains iota n. So n is as it is. That iota merge with this, so it becomes iota power minus n plus 1, because there is iota and there is iota power minus 1. Bases same powers add, so minus n plus 1. So this is your equation. Okay. Similarly, you have to take the derivative of this equation with respect to rho. So all are constants. Only you have to take the derivative of this Bessel functions, because this is a function of k rho. So what is only left with, you have to take a prime, because derivative of this, all other factor remains same. Now what you have to do, just you have to put the value of this and this in your general equation which you find, and taking common, because this is common, e naught I is common, and iota power minus n both common. Here iota left, then e power iota n phi is common, and 1 by rho is multiply here, so that's why rho. So these are common factors, and you know that uh, basically h equals to minus iota omega. You have to also multiply the cross product you take here, but this factor is also there, so iota omega mu, and these are the commons, and what you left inside is this. So this is your magnetic field incident equation. Okay. Now move, this is you find the incident, and this is you find the incident magnetic field. Now what you have to do is you have to find the E scattered and H scattered. So E scattered is same like E incident. The only factor is changes the Bessel function now change into the Hankel functions. Okay. This is your E scattered equation. As I mentioned you that this must be changed into the Hankel function equation. How you can, and other aspects should remain same. So in z direction, E naught S now is the amplitude. Initially there is E naught I is the amplitude for incident, and for scattered the amplitude becomes E naught S. And similarly, minus infinity to positive infinity summation iota power minus n same. Hankel function of first kind, k rho iota power e power iota n phi. Okay, this is your similar equation for the E scattered. But now there is a unknown which you must have to find first. There is E naught S, which is the amplitude of scatter. You have to find this, because initially there is E naught I. You also have to find your scattered electric field in term of I. So you have to convert this E naught S. So how you can find this? Here you have to use the boundary condition, which I mentioned you in the starting of the lecture, that as your walls are conducting walls, means the field inside is zero. If the field inside is zero, so the tangential components of electric field is also zero. At where? At rho equals to a. A is basically what you take the radius, and rho is the angle what x-axis make with the radius. Okay. So a tangential component of electric field are zero at the boundary, which is the rho equals to a. Now at this condition, your incident electric field plus scattered electric field must be equals to zero. So what you have to do, you have to equal your incident, which is this, equals to minus of other. So here is, you can see minus and scattered field, and this cancels with this, iota power minus n cancels with this, e power iota and phi cancels with this. You only have to find E naught S, so divide Hankel function to the other side, and E naught S becomes minus of E naught I, this, and why k rho, because as I mentioned in the boundary condition at rho equals to a, so rho converted into a. So this is the value of E naught S. Now you have to put this value here in scattered electric field. So I just put it the value, which is minus z prime as it is, E naught I summation. I put iota power minus n, and this factor, and Hankel function this, and e power iota n phi as it is. Now this is your scattered electric field final. Okay, in term of E naught I. Now the only term left is you have to find the scattered magnetic field. You have to use the same formula which we do for the incident field, which is del cross E equals to iota mu h. Now for the case of scattered, it becomes E scattered and here is the H scattered. We have to find H scattered, move iota omega mu to the other side, and here is del cross S. Now you again have to take the del cross E of S. Now you have to take the del of the E scattered. In previous you take the del of E incident. Here you have to take the del of E scattered. Same expects cylindrical coordinate system. So that's why 1 by h1 h2 h3 becomes 1 by rho. Okay, because h1 is 1, h2 is rho, and h3 is 1. When they multiply in denominator, it becomes rho. So 1 by rho. Unit vectors are rho, phi, z, and there is a factor of h2 which is rho. That's why there is here partial by partial rho, partial by partial phi, partial by partial z. And again you can see in the E scatter there is no x component and there is no y component. The only component is the z component and in negative. So that's why now it becomes negative of Ez. Understood? Now again you have to take the cross determinant you have to solve. 1 by rho, rho cap unit vector. This multiply by this minus rho Ez by rho phi minus rho cancels with rho, you will only left with phi, and this by this, partial minus partial Ez by partial rho, and when you take this 0, this 0, so only left with this. Now you have to find here again the derivatives of yeah, E of z with respect to phi, and you have to take the derivative of E of z with respect to rho. This is your expression of E of z. You have to take derivative of this with respect to phi, and then you have to take the derivative with respect to rho. Once you take derivative, you have to put the values here, and you have to see. Now let's take the derivative with respect to phi first. So this is your expression. Only phi we see is here. All other are constants which remains outside. When you take the derivative of e power iota n phi, so derivative is e power iota n phi, and the d by dx, so and the derivative of the power you are taking with respect to phi, so only left is iota n. N remains as it is, but this iota merge with this iota power minus 1, and there is iota also comes. Basis same powers add, so iota power minus n plus 1, so you can see. Okay, and all other are constant which remain same. Now you have to take the derivative of this equation with respect to rho. So here I take, you can see rho only here. All other are constant which remain same. Once you take the derivative of the Hankel function, because the Hankel function is a function of rho, so there is only a prime. Because there is rho, you have to take derivative, so it becomes prime. So here you can see it becomes prime, and all other aspects are same. Now this is your this value, this is your this value. Now you have to put these both value inside your this expression. After putting, you can easily get your del cross es, and after dividing it by iota omega mu, you can get your h scattered. So here you can see del cross es. I just multiply, I just put this value here and this value here. So after putting values, many aspects are common, like E summation minus infinity to positive infinity is common. E naught I is common in both. Iota power E and iota and phi is common in both. And this factor is common in both. So it comes outside. Iota power minus n is common, and only iota remains inside, and these factors are common. And there is a factor in divide iota omega mu. Why? Because you know that one, if you find this is the answer, and beside there is a factor iota omega mu, so that's why this also be there. So iota omega mu and all the commons which I take, and inside only left with iota which remain here, and this 1 by rho, this 1 by rho, and rho prime, and the Hankel function of k rho. And similarly here the left is only minus phi unit vector, and Hankel function, here is Hankel function prime. Okay, here is the Hankel function prime, and k of rho. So this is the expression of h scattered. Okay, so that's it for how you can solve the fields for the scattering of a perfectly conducting cylinder. So that's all for today's lecture. If you have any question, you can just leave a comment below, or you can directly contact me. We will upload more interesting videos for this course. Probably this is our last lecture of this advanced electromagnetic field and waves. I should thank you for watching the full playlist of electromagnetic field and waves. Now we have to move on towards more interesting new courses. So that's the end of this course. So from my side, thank you, take care, and Allah Hafiz.